Hi, let us get started. So this is sixth session. Okay. Last time I think Aman had a question on this index notation, right? So is it clear to you, Aman, right now? Or you still have doubt on this index? You are confused about what is this rho nu sigma index and why there are two different indices, right?
Yes, so I like this omega mu nu and j mu nu are contracted. So I was thinking
Yeah, so
index matching. I was thinking
yeah, so
like how
okay, so
rho
yeah,
sigma
yeah,
is.
yeah. So I understand. We will go over it slowly, and yeah, we'll understand this particular thing. So what I was writing here is not correct. This J has nothing to do with this particular operator. Okay, so let me correct myself. So here, whatever is written on the right hand side. Okay, so we'll do that on the other PDF, but that was not correct. I just rubbed it. We will do it from the beginning. And one more thing I said which was not correct last time. So here I wrote 0 1. Okay, so this should not be like the entire matrix. So this is a matrix, right? This is a 4 by 4 matrix. So lambda, when we write mu and nu, it means mu denotes the row index and nu denotes the column index. Okay, so writing 0 1 here would imply we are looking at the 0th row and first column, so this particular element. So this notation is incorrect. This is still lambda matrix, but it corresponds to this lambda. This is lambda matrix, so mu nu, but it corresponds to boost along x1 direction. Okay, in order to specify which particular Lorentz transformation we are talking about, we have to bring in two more indices, which is what is done here. Like two different indices you can see here. So one index is for row and column of the particular matrix, and another is to specify the Lorentz, which particular Lorentz transformation you are talking about, whether you are talking about boost along x1, x2 or x3, or you are talking about rotation about xy plane, yz plane or xz plane. So these are the 6 Lorentz transformations, right? So okay, so we'll do this now, and yeah, so and this is also mu nu, I have corrected here. Okay, one more thing before we get started. Here what we were doing last time, we considered infinitesimal Lorentz transformation, like lambda equal to identity plus some infinitesimal parameter, and then we checked how the field gets transformed. So this was delta phi, and the Lagrangian transforms by this total derivative. So we found out what is the conserved current using the rule that we did for Klein-Gordon Lagrangian. We found out total linear momentum, total energy. So that same method we were using here to find out what is the conserved current if the infinitesimal Lorentz transformation is a symmetry of your problem. And we know that zeroth component of the current, if we integrate over whole space, we get the conserved charges. So we found out what is the conserved charge corresponding to boost and what is the conserved charge corresponding to rotation. So that is Q0i is corresponding to boost, and what is Qij? Sorry, I must have written it somewhere. Just a moment. So Qij was the charge corresponding to rotation about Ij plane. So this is Qij. Sorry, this is not Qij. Qij will be integration of this over d3x. Yeah, I probably forgot to write that. Let me just write that down. So Qij is integration d3x j0 ij. Okay. Okay, so yeah, so let's look at Lorentz transformation again, and we will do everything in that notation so that everything gets clarified to you. So yeah, so you know the rotation in 3 dimension. If you look at the generators are angular momentum. So Jij is xi pj minus x j pi. Okay, and when we want to promote it to 4 dimension, the generator are basically the generators corresponding to Lorentz transformation, x mu p nu minus x nu p mu. Okay, where jij, so you can see this is antisymmetric under the exchange of mu and nu indices. So this is equivalent to I del x mu del nu minus x nu del mu. Okay. So Jij corresponds to rotations and J0I are the generators corresponding to boost. Now we can figure out what is the Lie algebra satisfied by these generators. So we need to compute this commutator. So you can substitute. So you can substitute that operator here, and you know the commutation relation between x and p. So you have to use those, and then you can find out what is the form of this particular commutator. P sigma minus x sigma p rho. Okay. So the commutation relation between x p will be minus I eta mu nu. Okay, there is minus sign because remember our convention is, just a moment. Can you review from starting this joint? We haven't done much yet. We have started looking at Lorentz transformation. I'm just telling you the generators corresponding to Lorentz transformation. Okay. Yeah. So this J mu nu are the 6 generators. So you can see that it is antisymmetric under mu and nu indices. Mu nu runs from 0, 1 up to 3. So basically you have 6 independent generators, right? Because J00, J11, J22, J33 all will be 0, and upper triangle, J01 is same as minus J10. So you have 6 generators. Among those, these 3 are correspond to rotation when I and J runs from 1 to 3, and these J0I correspond to boost. Now I'm trying to derive what is the D algebra satisfied by these generators of Lorentz transformation. Okay, so I'm saying that here the commutation relation between x and p is minus I eta mu nu, because our convention is eta is 1 minus 1 minus 1 minus 1. Okay, so you can see that with this minus sign you get the correct commutation relation, that is x px equal to I and et equal to I. Okay. So this is just a matter of doing this calculation. X rho p sigma minus plus x mu p nu x sigma p rho okay. Now let us sorry, this will be a bit lengthy but straightforward. So p nu x rho p sigma plus x mu, sorry, so x mu p nu x rho, the next term would be x mu p sigma x rho p nu. Okay, order is important, plus that is coming from the first commutator only, these two terms, and the next commutator will give you similarly two terms, p mu x rho minus x nu p sigma minus x mu plus x mu p rho x sigma p mu. Okay, so this is equal to, so the first commutator is x mu p sigma eta rho nu rho minus p nu eta mu sigma x nu p sigma eta mu rho this will become plus minus x mu p rho eta nu sigma plus x sigma p nu eta mu rho plus x nu p rho hopefully I didn't make a mistake. Okay, so let's see. So this term along with this one will give us, so let's underline, these two terms will give us okay, I forgot to write I everywhere, so I is multiplied. Okay, so yeah, so those two terms will give us j mu sigma eta nu rho. Okay, and then this term and this one will give us minus j rho nu eta mu sigma okay, then this term along with this one give us minus j nu sigma eta mu rho, and the remaining two terms j rho mu eta mu sigma. Is this clear, everything? Let me just check whether this is correct. Yeah, any questions?
Yeah, so I don't have a question. It's kind of clear, but can you do one quick run through of what you did from the beginning? Since it was so elaborate, can you like
Yeah, just a moment. I'm just
quick run through? Yeah,
I'm
thanks.
just checking if it is correct. Rho nu. Yeah, so in book it is plus and this is nu rho, so it's fine. And the last term is yeah, so this is fine. Okay, just to match with book, let me do that. So I'm doing this plus and flipping this sign, nu rho, because you know it's antisymmetric, and this is minus and flipping this. Doesn't matter, but anyway. Yeah, so what we have done here is, so this is the 4-dimensional analog of the rotation generator that you know in 3 dimension, which are the angular momentum generator. Sorry, angular momentum are the generators of rotation in 3 dimension. In 4 dimension it becomes this, the analog, and 3 of them are rotations and 3 are the boosts. Generators corresponding to rotation, generator corresponding to boost. And then we are just trying to figure out what is the Lie algebra satisfied by these Lorentz transformation generators. So we know this, right, in quantum mechanics, that Jij k equal to epsilon ijk j, sorry, what did I say? So yeah, so use a different notation, maybe Li. Yeah, Li Lj equal to I epsilon Ijk Lk in 3 dimensions. So that is the angular momentum algebra. So we wanted to see what is the algebra satisfied by the generators of Lorentz transformation. For that we are just computing the commutator of J mu nu and J rho sigma, and if you compute that commutator, that turns out to be this. So this is the Lie algebra satisfied by the generators of Lorentz transformation. If you find out any representation which satisfies this particular commutation relation, so that is a representation of your Lorentz transformation. We will talk about two such representations today. One is vector representation, another is Spinor representation. Spinor representation is a representation under which a spinor transforms, and vector representation are the representations under which a 4 vector transforms.
Okay.
Yeah. J rho sigma. Okay. So let's box this. So okay. Now let's talk about the vector representation. Okay, so we will consider a particular matrix, 4x4 matrix J mu nu. Let's use a different J, okay, so as to not to confuse with what J we wrote there. So let's use M. Just a moment. Should I use M? Yeah, let's use M. M mu nu. Okay, rho sigma. And yeah, so the definition is, so this is anti-symmetric under the exchange of mu nu. Okay, so what we are doing basically is that there are 6 generators of Lorentz transformation. Now we are trying to write down a finite dimensional representation. So we are trying to write down a matrix representation which will a particular matrix representation corresponding to Lorentz transformation, which actually satisfy this commutation relation. Okay, so when you plug in this particular matrix in this commutation relation, it has to satisfy this. So that then only you can say that this is a representation corresponding to Lorentz transformation. So the the matrix is as follows: eta mu nu sigma minus eta nu rho eta mu sigma. Okay, so this is basically anti-symmetric under the exchange of mu nu indices, and it is also anti-symmetric under the exchange of rho and sigma indices. Now some of you might get confused why there are so many indices. So this mu and nu, this will basically tell you that there are 6 such matrices, 6 such 4x4 matrices. Okay, and this rho sigma are basically denoting your row and column. So basically we will be in a what we will be doing, we basically need a representation like this, one index up and another below. So what we can do is lower that sigma index by this. So yeah, let me just do that, then I will make one comment. So eta sigma, let's write lambda. So that will be eta mu rho, eta nu sigma, eta sigma lambda, eta mu sigma, sigma lambda. So this becomes rho lambda, eta mu rho, delta mu lambda minus eta nu rho delta mu lambda. Okay, yeah. So in this language you cannot see the antisymmetry under the exchange of rho and lambda indices, but you can still see that this is antisymmetric under the exchange of mu and nu indices. So it means you have, so when mu and nu both are running from 1, 2, 3 up to 3, so you have 6 such matrices. There are 6 M matrices, and it turns out that these are the generators corresponding to the infinitesimal Lorentz transformation. How? Let's illustrate that. Yeah, so how let's illustrate that. So let us consider M. Okay, just repetition. So this rho and lambda denoting the row index and column index of the matrix M, and mu and nu denoting there are 6 such matrices because it is antisymmetric under the exchange of mu and nu. So yeah. So let's consider mu equal to 0 and consider nu equal to 1. Okay, so M01 rho lambda, let me write rho sigma, that is eta mu rho delta 1 sigma minus, just stop me at any point if you are not following anything. Okay, so eta 1 rho delta mu is 0 sigma. Okay, so let's write down the corresponding matrix. Okay, so mu nu goes from 0 up to 3. Likewise, rho lambda also goes from 0 up to 3. Yeah, just let me write down 2 in between. Yeah. Okay, so what will be the matrix? So the first element is rho equal to 0 and sigma also 0. So you can see this term will be 0 because this will become 1, 0, and from the second term also this will be 0, right? Because rho is 0 and sigma is 0, so this will become 1 but this will be 0. So the 0, 0 component is 0. Likewise, you can figure out what is the 0, 1 component. So 0, 1 component is 1, as you can see, right? 0, 1 component is 1 coming from this term, and this term is still vanishing because when you substitute 0 here it becomes 0, but you 0, 1 if you substitute here you will get 1. Okay, so 0, 0 for all other elements in the first row, and second row first column, so that means rho is 1 and sigma is 0, so this term vanishing, and when you put rho 1 sigma 0, so from that term you will get, what will you get? You will get eta 1, 1 because this is 1.
No, nothing. I was just going to say eta 1, 1. No, nothing.
Yeah, eta 1, 1. So there is one minus sign, and eta 1, 1 is minus 1 for us. So ultimately we get plus 1 here. and then you can check all other elements are 0. Okay, now let's recall the Lorentz transformation for boost along x1 direction. So how does the a 4 vector transform under boost along x1? So let's write it down. So x0 prime is gamma x0 minus beta x1. Okay, x1 prime is gamma x1 minus beta x0. x2 prime is equal to x2 x3 prime okay. So x prime mu is lambda mu nu x nu, right? And what is the lambda mu nu matrix corresponding to this boost along x1 direction? Lambda mu nu is basically lambda mu nu is equal to gamma minus beta gamma 0 0 minus beta gamma and 1 here, right? So clear up to this. Now we said that this matrix corresponds to infinitesimal, corresponds to the this matrix is basically the generator corresponding to infinitesimal Lorentz transformation, and the particular Lorentz transformation being a boost along x1 direction. So this lambda mu nu we can express as cos hyperbolic xi minus sin hyperbolic xi, where xi is called rapidity, minus sin hyperbolic xi now consider xi to be infinitesimal. So you can Taylor expand cos hyperbolic and sin hyperbolic. What you get is 1 here minus xi there, then minus xi 1. Okay, so this you can write as 4/4 identity, 4/4 identity minus xi times this matrix 1 0 0. This is what we had, right? That is nothing but this matrix M01 rho sigma. So instead of calling this xi, let's call it so this is M01 rho sigma, where rho and sigma denoting the row and column indices, and 01 denotes the, let me write that, generator corresponding to boost along x1 direction. Okay, so this is infinitesimal, so that's why we expanded it up to first order in xi, So the finite Lorentz transformation will be, so finite Lorentz transformation lambda rho sigma will be exponential of minus I over 2 mu nu m mu nu. Okay, so the whole thing will be a matrix whose indices are rho and sigma. So yeah, Aman, now is it clear to you? So this is the same mu nu index and rho sigma index you had in the lecture, right? So okay, let me write one more thing and then you can let me know. So any 4 vector any 4 vector transforms under the Lorentz transformation as, so any 4 vector, let's call it u alpha, u rho. So under Lorentz transformation that becomes lambda rho sigma u sigma, okay, which is equal to that this thing. So exponential of minus I over 2 omega mu nu m mu nu rho sigma rho sigma. If the transformation is infinitesimal, then this omega, you can expand this exponential up to first order in omega. So you have identity matrix, 4 by 4 identity matrix with indices being rho and sigma, minus I over 2 omega mu nu m mu nu rho sigma u sigma. Yeah, now let me know, Aman, whether you can understand this. This is the same thing what you were showing me from the lecture. Do you have any confusion on this? On the indices now?
I understood that matrix part, but if we write in form of answer like differentiation, like if we write not matrix but like in terms of derivative.
In terms of derivative, you mean this j mu nu that we had here?
Yes.
No. Okay. So yeah. So that's why I used a different notation m here. So this is the finite dimensional representation of Lorentz transformation. This is giving you a finite dimensional representation of Lorentz. By finite I mean you can write down a 4 by 4 matrix. But for this operator notation, you don't have that. So that's why we are going to this particular representation, and we are saying that look, this is the Lorentz transformation. Sorry, so this is the Lie algebra satisfied by the generators. So if you can find out any matrix which satisfies the same algebra, then that matrix corresponds to the representation of Lorentz transformation, and this is one such case. So this is one such representation, and you shouldn't confuse this m mu nu with this j mu nu. So in the lecture, professor used this j mu nu index for, sorry, j mu nu notation for this vector, this operator, for this operator, and he was probably using a different notation like curly j mu nu, which is what is done in Peskin, I think, Peskin also. But this curly j mu nu with rho sigma index is different from that j mu nu operator what you have here, the analog of rotation in 4 dimension. Okay, so do you get what I'm saying? So you shouldn't write this J mu nu with rho sigma, I think. But that rho sigma is being written for this vector representation where you have a 4 by 4 matrix, and for that matrix, in order to denote the row index and column index, you need to bring in two more indices, this rho and sigma. Is this clear to you? No?
Yes. Yes.
Yeah. Okay. So this is how a 4 vector transforms under Lorentz transformation. Okay, let's see if there is anything more to say here. Then we will move on to Spinor representation. So, okay, so one more thing we can just do for our satisfaction. Maybe we can write down what is M12. Okay, so that would imply rotation in the xy plane. Okay, so that M12 that we will obtain from this vector, this matrix representation, that should correspond to what we get by a rotation in xy plane which mixes x and y coordinates. So let's do that. So let me copy this and we will just write it down for okay. So when mu is 1 and nu equal to 2, so you have M12 rho sigma, so that is eta 1 rho delta 2 sigma minus eta, so nu is 2 delta 1 sigma. Let's write down the matrix. Okay, so I think, yeah, I think there is I here. Okay, so there is I in this definition. Just let me insert that I. Okay. Yeah. Now it makes sense. Yeah, because here M01 will have one I coming from the definition, and that I will get multiplied with this I, giving you -1, and so it will become plus here. Yeah, I think there is a plus minus mismatch with what I am writing here and what we have obtained here, but that doesn't matter because you can always take this to be plus and so on. But otherwise it's fine. So this is M01. Okay, I think everything is fine. So this will be minus I. Sorry, I think there is no mismatch. Just let me check. So this matrix, so M01 rho sigma is I times this matrix. So this matrix will be minus I times this. So you will get plus basically here. So it's fine. There is no mismatch. Sorry, hopefully I didn't confuse you. Is everything fine? Okay.
Yes.
Okay. Okay, and so this xi here is basically omega 01 that we have here. So omega 01 is getting contracted with M01. I mean here is no contraction, it's just that particular element, but here it's the contraction, and omega 01 will be contracted with M01. Okay. Sorry, why do I feel still there is something missing? Just a moment. So minus I. So this lambda mu nu will be identity plus I. Oh yeah, it's fine. Just let me write this down. I'm getting confused. So this is identity 4 by 4 minus I omega 01 m01 rho sigma, and that is what we will get from here also if we expand it. Okay, and notice one more thing, why there is a by 2 factor, because omega mu nu is antisymmetric under the exchange of mu and nu indices. So if you expand it, you will get minus I over 2 omega mu nu m mu nu. But remember, mu nu is antisymmetric for this omega as well as for this m. So omega 01 m01 is same as omega 10 m10. So just to avoid counting two similar terms, we are dividing by 2, and this summation is basically this summation is summing over all indices. Okay, so this 2 is just to avoid over counting. Okay. Okay, so let's proceed with this mu equal to 1 and mu equal to 2 case. So what will be the elements now for this matrix? Let's see. So for 0th row, everything will be 0. Also 3rd row, everything will be 0, as you can see. And only this 2 by 2 column, 2 by 2 box, there will be non-zero elements. So let's see. This element corresponds to rho equal to 1, and sigma equal to 1, right? Rho, sigma both 1, so this term doesn't contribute. How about this term? So for this term, rho is again 1 and sigma is also 1, so again 0. So this term is 0, which implies this term should also be 0 because this is an antisymmetric matrix. And so this term would correspond to rho equal to 2 and sigma equal to 2. So if we put 2 here, that gives 0. If we put 2 here, that gives 0. Okay, so that's 0. I just rechecked it because when we write rho here and sigma here, that antisymmetry property may not always hold, because as you can see here, so this is an important point. Let me just point out. So this m01 rho sigma is not antisymmetric, right? Meaning if you take whole transpose of this matrix, you are not getting minus of the matrix. So, but if you multiply it by, let's say, eta sigma lambda, that will, the matrix that you will get after multiplying by 1 minus 1 minus 1 minus 1, you can check, probably that will be antisymmetric under the exchange of rho and lambda indices. But this matrix is not antisymmetric, and this will have a consequence as we will come to. Okay, so let's see what are these two elements. So what is this element? So this is rho equal to 1 and sigma equal to 2. So that's 1 coming from the first term. No, minus 1, because eta 1 is minus 1. Okay, and this element, so this corresponds to rho equal to 2 and sigma equal to 1. So 2 and 1, if you substitute here, you get plus 1. Okay, so there was I. Sorry, did I not put I there? Oh, after I copied, probably. I put I anyway. So I times that matrix. So now you can see this this matrix is basically Hermitian, right? This matrix is Hermitian. If you do dagger, you will get minus I here, and this will get flipped. So this is basically Hermitian. So let me just write that down. M12 rho sigma whole dagger M12 rho sigma. And this is true in general. In general, if you write down ij, where I and j goes from 1 up to 3, and you take dagger, you will always get mij rho sigma. So the generators corresponding to rotation are always Hermitian, but okay, so I think here I was talking about real, but these are complex because of this I. So I wanted to mean that if you take dagger of this matrix, you will not get that matrix, but you will get minus of that matrix. So M01 rho sigma whole dagger is equal to minus of M01 rho sigma. And that is true in general. By that I mean M0I rho sigma dagger is equal to minus of M0I rho sigma. Okay, so this was aside, which will be useful to us later. But now let's see the matrix that we have obtained from this representation, whether it matches with what we would expect when we perform a rotation in the xy plane. Okay, how does that change? So x0 prime remains x0, x1 prime become cos theta, x1 minus sin theta x0, x2 prime is sin theta x1 minus cos theta, sorry, why 0 here, it's 2, and x3 prime is equal to x3. So what is the corresponding Lorentz transformation matrix? Lambda mu nu is 0 0 0 0 cos theta minus sin theta 0 sin theta cos theta 0 0 0 0, sorry, 1 here and 1. Okay, so again this is nothing but x mu prime is equal to lambda mu nu x nu, and this lambda mu nu corresponds to rotation about x1 x2 plane. Corresponds to rotation about x1 x2 plane. Okay, now if the transformation, if your angle theta is let's say infinitesimal, then you can expand, Taylor expand again, and what you get is lambda mu nu, that becomes equal to 4 by 4 identity plus theta times 0 0 0 0 0 minus 1 0 1. Okay, and that is nothing but what we have obtained here, this M12 rho sigma. So this is equal to minus I times M12 rho sigma. I think the sign mismatch is happening now because what we see. I get a minus I here. Anyway, don't bother, because in this parameter you can take that minus sign inside and redefine your parameter, so it doesn't matter, just a matter of convention. But I think the idea is clear. So this M12 you are getting when you perform a rotation about x1 x2 plane. Is it clear to you what I'm trying to say? So we have checked for rotation and for boost. Okay, and this is an important fact that we have just checked, that these matrices corresponding to rotation are Hermitian, but corresponding to boost are not anti-Hermitian. So let me just write that down because it's important, and we'll come back to it. So so this is Hermitian. This is anti-Hermitian. Okay. Now let's proceed and define something else, which is called Spinor representation. Okay. Before we do that, let me pause and ask if there are any questions.
Can you please write operator, differential operator, expression for J? Like I have problem in indices, like where will be up and down.
Sorry, differential operator.
Like of rotation, J meaning.
These are finite dimensional representations corresponding to Lorentz transformation, but so you can write down the corresponding matrices, and we already wrote down. Sorry, I think the scrolling up and down gets irritating for you, I understand, but sorry, I can't help. So here, see, this J mu nu, this is the corresponding operator. Okay. So is that what you wanted to say, Aman?
But like here will be not rho sigma, like here will not be able to take rho up and sigma down element, like what we were taking in matrices, like if there was rho index up and sigma index down.
So that is the matrix index. Here it is not the matrix index. It is showing you. I mean, we are not writing down the corresponding matrix. I don't know. Do you want to mean this J mu nu here like that?
Like if I have to write this in terms of like x, if I want to insert it so that I can like get transformed, like transformed x equal to generator, which is like identity minus I generator into x sigma. Like if I want to write whole expression, like how will I write this? I have to take eta, like to make one down so that I can contract with x. Like if I want to like write infinitesimal transformation, but I have to apply it on x so that it becomes x prime. So this expression I have to write, then I have to like take one index down by multiplying eta. Like in matrix it is rho sigma and s x sigma, which is sigma is getting contracted, giving x prime rho.
Sorry, I'm not sure if I followed what you were trying to say. Sorry, I couldn't understand what you were trying to say. Would you like to repeat it?
I want to say like if I want to write To write lambda rho sigma, like it is lambda rho sigma
wait. So you want to write lambda rho sigma.
in operator notation, differential operator.
Wait, so you want to write the differential operator notation of lambda rho sigma. Okay, so wait. I mean, lambda rho sigma is basically, so this is a Lorentz transformation. You get it. So this is a finite Lorentz transformation. You get it when you exponentiate the corresponding generators, right? So this is a, I mean, it has a matrix representation, like 4 by 4 matrix. It is a 4 by 4 matrix. So you are performing Lorentz transformation in Minkowski space, which is a 4 by 4, 4-dimensional space. It mixes space and time. If you are performing boost, and if you are performing rotation, it mixes your space coordinates. So the Lorentz transformations are defined like this for rotation, and Lorentz transformations are defined like this for boost. And so lambda is a matrix, and we are trying to write down the generator, the matrix form of the generator. Now we know that Lorentz transformations are giving us, so Lorentz transformations are rotations and boosts, and the generators are nothing but these operators. And we also know what is the Lie algebra satisfied by those operators. Okay, this is the Lie algebra. And since we cannot write down the matrix representation for that operator, we are coming up with a vector representation and Lorentz transformation, and Spinor representation, which also satisfy the same Lie algebra. So it means these representations are nothing but the representations corresponding to Lorentz transformation. And we have explicitly checked that these are indeed the Lorentz transformation generators. These are generating the Lorentz transformation, in the sense that that matrix is taking you away from the identity when you are performing a boost along x1, and when you are performing rotation along about xy plane. So this lambda is a matrix. I'm not sure if it has a operator representation, operator form which you are trying to find out. I'm not sure if there is any, but there might be.
Like if it was infinitesimal, like you have told, like angular momentum, like it is infinitesimal. If it is, then
if it is infinitesimal angular momentum, is that what you are saying?
like identity plus like generators like angular momentum, like so I was like you have to contact index. I
Okay.
want to.
Sorry, just a moment. You are okay. I'm saying these are the Okay, I'm saying these are the infinitesimal generator corresponding to Lorentz transformation, and you are trying to see whether that can be mapped to J mu nu we had earlier. Is that what your question?
Yes, I want to write this expression because I have index. I want to see like how we have to contract, like to multiply eta, because here both indices are up if you write in J mu nu, but in lambda it is one up and down.
So as I said that m, so this is different from this m mu nu. I don't know if you are trying to equate this with J mu nu. You are probably trying to equate this with J mu nu, but I mean, as far as I know, these two are different. We are coming up with a 4 by 4 matrix of hat, and then we see that this satisfies this commutation relation. Okay, and we also can see that these are nothing but the matrix representation of the Lorentz transformation generator. Okay. I don't know if your doubt is still clarified. should I move on? You have anything else to ask?
Like if this lambda mu nu, if infinitesimal it is, like we can write in this if in form of generators of like rotation, like differential operators. Like it has indices both up, no? Rho sigma, lambda, rho sigma.
Yeah, this is what I'm telling you. I'm not sure whether this lambda has a operator expression. I'm only aware of this matrix representation of the Lorentz transformation. Matrix representation of this Lorentz transformation. I'm not sure if it has a operator expression. I will take a look at references. If I get to see anything, I'll let you know. Okay.
Yes.
Okay. Okay. So let's now get to Spinor representation. By the way, operator representation of the generators corresponding to Lorentz transformation are nothing but those J mu nu only, because J mu nu these are the operator representation of the Lorentz transformation generators. Okay, these are the rotation generator, these are the boost generator, and they satisfy this commutation relation. And you cannot write a matrix representation for these, so that's why we came up with this. So I don't see anything confusing here, but anyway, just give it a thought, and if you still have questions, let me know later on. Okay, so we are now coming back to Spinor representation. So we are trying to find out a different representation which still satisfy that same commutation relation satisfied by the generators of Lorentz transformation, J mu nu. Okay, so for that we first introduce Clifford algebra. I think these are done in the lectures. Are these done in the lectures? Can somebody let me know? So Clifford algebra, introduce these 4 by 4 matrices gamma mu. So gamma mu, which satisfy this commutation relation gamma nu is which is anti-commutation relation. This is equal to 2 eta mu nu. Okay, and it's the identity. And the claim is that if we take commutation relation between this gamma mu and gamma nu, whatever we get, that satisfies that commutation, that satisfies that Lorentz Lie algebra. So it satisfies so that Lie algebra, we will let us just find that out explicitly, that it indeed satisfies that Lie algebra that we want it to satisfy. Before we do that, let's see what is gamma 0 square. So gamma 0 square will be identity. Gamma I square will be -1, right? Okay. Yeah. So now let's see what is the commutation relation. Rho sigma. Okay, so this can be rewritten as, so when mu equal to nu, this is 0 as it is obvious, 0 for mu equal to nu, and when mu is not equal to nu, what do we get? So we see that, so when mu is not equal to nu, so from this Clifford algebra we can see that for mu not equal to nu, the right hand side is 0. So that means gamma mu gamma nu is equal to minus gamma nu gamma mu. So this becomes I over 2 gamma mu, and it has a nice way of writing. So this is equal to I over 2, sorry, what have I written? We can write this down as minus I over 2 gamma mu nu. Let me see if I've written it correctly. So when mu equal to nu, this will become gamma mu square, okay, and this will become 1 when it's mu nu equal to 0, and that gets cancelled, and it will become minus 1 when mu and nu both are I, and that will again get cancelled with this. I think it's correct. Now let's figure out what is the commutation relation. So we begin with rho not equal to sigma, otherwise this is anyway 0, right, if rho becomes sigma. So let's rho not equal to sigma and then try to figure this out. So this becomes I over 2 gamma rho gamma sigma, okay. So I over 2 is mu nu gamma rho gamma sigma minus gamma rho is mu nu gamma sigma, okay. So let's figure out what is this commutator. Is mu nu gamma rho, what is that? So for this to be non-zero, of course mu and nu should not be same. So I over 2 gamma mu gamma rho. We know the anti-commutation relation between the gamma matrices, so it's better that we try to write down the anti-commutation rule. I mean, we try to write down what we have in terms of the anti-commutator. So it is gamma rho gamma nu gamma, sorry, gamma mu gamma nu gamma rho minus, okay. So we can write down I over 2. We can form an anti-commutator with these two and another anti-commutator with these two, so that the extra terms coming will get cancelled out. So what I mean is this and the extra term we have to subtract. So the extra term is gamma mu gamma rho gamma nu. Let me know if you don't if you have difficulty following anywhere. Minus gamma yeah, so we need a term like this. So if we flip this and this, then we will get the same term. So let's write down the anti-commutation between gamma rho and gamma mu, and then add that extra term. Extra term is gamma mu gamma rho gamma nu. So you can see this is getting cancelled with that, and now you can use the Clifford algebra, which was 2 times eta mu nu. So 2 times gamma mu eta nu rho minus 2 times eta rho mu gamma nu. Okay, so I times, I'm just rewriting. Okay, I hope it's clear. Okay, now let's substitute this. Okay, now let's substitute this here and see what we are getting. We are having I here. Okay, well, let's proceed. So it's S mu nu S rho sigma is equal to, let's just copy. So equal to I over 2 another I coming, so that will give us a minus 1 outside, and this was S mu nu gamma rho. Okay, gamma mu gamma sigma, eta is just diagonal, right? So it we can the order doesn't matter for eta. It will commute with all the matrices. Then eta nu rho minus the second term is gamma nu gamma sigma eta rho mu. Okay, minus the term will give us, okay, instead of rho now we have sigma. Okay, so gamma mu eta mu sigma plus gamma rho gamma nu eta sigma mu. Okay, so yeah, now the remaining thing that needs to be done is as follows. You can see you have this gamma mu gamma sigma gamma nu gamma sigma appearing everywhere, and we don't have any restriction between this mu and rho, right? So they can be same or they can be different. So that means we should use this particular expression here to write down what is gamma mu gamma nu. So is mu nu so from here we can see that gamma mu gamma nu is equal to I is becoming confusing to me. So I times gamma mu is equal to 2s mu nu plus I eta mu nu. Okay, or yeah, so what we can do is this minus 1, let's write it as I square. Okay, one I we will keep outside and another I we will use to write this down. So gamma, okay, so let's do that. Okay, so this is equal to I over 2 2 times S mu sigma eta nu rho that we have here. Then the next term, that is this one, will be plus I gamma, sorry, we are replacing gamma mu sigma, so we have eta I eta mu sigma eta nu rho. Okay, that is the first term. Now the second term, we have gamma nu gamma sigma, so this will give us S nu sigma eta rho mu minus I eta nu sigma eta rho mu. Okay, minus 2s rho mu eta nu sigma minus I eta rho mu eta mu nu plus 2s rho nu eta sigma mu plus I eta rho nu eta sigma mu. Okay, see all these terms are getting cancelled out. Sorry, yeah, those two terms, no, those two terms are not getting cancelled out, but this term is getting cancelled out with which one? Did I make a mistake? Sorry, pardon me. Yeah, okay, so this eta rho nu, we have eta rho nu here, and eta sigma mu, sorry, both are coming with plus sign. That shouldn't be the case. Oh, what is happening here? Just a moment. So we are, yeah, there is plus here. Okay, there is plus, right? There, we are just writing this commutator. So this with that plus this with that. So there is plus in between, so that plus sign is making everything long. So let me try to incorporate plus here, so which means this is plus and that is minus. Okay, and that means the last two line, this is plus plus and this is minus minus. Now I think it's fine. So this getting cancelled with that. Okay, and likewise this is getting cancelled with, oh, oh, okay, sorry, So this eta is nothing but this eta. So nu sigma. So these two are again getting cancelled out. So you can see what we have is nothing but that same commutation relation satisfied by J mu nu. Plus is rho mu eta nu sigma minus is rho nu eta sigma mu. Is everything okay? Any questions? Are there any questions? So just to compare, let's just copy. Okay, so it's the same, right? Yeah, I think plus minus interchange has happened. So I can make this plus and interchange this mu rho, and that is minus plus. So I can also interchange this one and make it mu rho. Okay, so therefore these are called Spinor representations. The reason is that any 4-component field transformed under S mu nu is called Dirac spinor. And the corresponding representation is called Spinor representation. So a Dirac spinor psi alpha under Lorentz transformation. Okay, so we haven't written down what is the finite, so call it, so I'm using the Piskin notation. So lambda half is exponential of minus I over 2 omega mu nu is mu nu. Okay, so rho sigma. This half is to convey the fact that the quantization of Dirac spinor will give us spin half particles, which we will do eventually. Yeah, but yeah. So what I was saying is any 4-component field transformed under S mu is called Dirac spinor. So the Dirac spinor would transform as alpha, beta, psi beta. Okay. Okay. And so this is also x dependent. Now, what we can do is, yeah, we can write down the basis. Are there any questions at this point? Is this clear what we have done for the spinor representation to everyone? Okay. So okay. S mu nu. Let's look at the properties of S mu nu. Then we will write down Dirac equation. So it was defined as I over 4 gamma nu So the while basis is as follows: gamma 0 0, which is a 2 by 2 0, are the Pauli matrices. So sigma 1 is, just for completeness, let me just write down. One zero zero minus one. Okay, and let's see what is Sij and S0i. So this is called while or chiral representation. This above representation. Okay, now let's see what is Sij. Sij is I over 2, let's say I not equal to j, gamma I gamma j, and what is gamma I gamma j? It's I over 2 sigma I 0, sorry, 0 sigma I minus sigma I 0, 0 sigma j minus sigma j 0. I over 2 minus sigma I sigma j okay, and sigma I sigma j is equal to I epsilon ij k sigma k. So this is 1/2 epsilon ij k sigma k 0 sigma k. Okay, so you know that Sij, so we are, so note that here we have suppressed the row and column index. Okay, we have just written down Sij, but these are matrices, so you can put row sigma index also. These are all 4 by 4 matrices. So that dagger so these are Hermitian, as you can see, because Pauli matrices are Hermitian. Let's look at the Spinor representation corresponding to boost, so which would imply S0i. What is S0i? I over 4 gamma 0 gamma I, right? So gamma 0 gamma I will be I over 2. So I over 2, gamma 0 is 0 identity 0, and gamma I, what is gamma I? 0 sigma I minus sigma I 0. Okay. So we get first row, first column giving minus sigma I, first row, second column giving 0. Right? So it's easy to see that rho sigma, if we take dagger, we get minus of S0I. So these are, so the Spinor representation, so the generators corresponding to Spinor representation of Lorentz algebra. No, sorry, what did I say? Sorry, I was trying to say that the generators which correspond to boost for the Spinor representation of Lorentz transformation, those are anti-Hermitian. Anti-Hermitian. Okay, so what does this mean? It means that the finite representation, sorry, which we wrote as lambda half rho sigma, what was that? That was exponential of minus I over 2 omega mu nu S mu nu rho sigma, right? If we take dagger, if we try to see what is lambda, dagger, lambda, it will not be identity, right? This will, what I mean to say is that this matrix under which a spinor transforms, that is not unitary, because of the fact that S0I dagger is becoming minus S0I. If this generators corresponding to boost were also Hermitian, then you would have gotten plus I here, and this S mu nu dagger becoming S mu nu, and then this lambda half would have become unitary matrix. But that is not the case. Okay, and this doesn't matter because the Dirac spinor is again a field, so it can transform under non-unitary matrices as well. Okay, so this is an important point to make. And now, so having said all of this, let's now write down the Dirac equation. Okay, let's write down the Dirac equation. And maybe in the next class we can see the corresponding Lagrangian of the action, and then we can do some problems on this gamma matrices. So Dirac equation is a first order equation, and that is I gamma mu del mu minus m acting on psi equal to 0. Now let's check that this is invariant under Lorentz transformation. So let's do that, and then maybe we can stop. So how would it transform under Lorentz transformation? We know already how psi transforms under Lorentz transformation. It transforms as, sorry for scrolling up and down again. So this is how the Dirac spinor transforms. So the first term also should transform in the similar way, so that the entire thing becomes Lorentz invariant. Yeah, someone had to say.
Why there is lambda inverse x in psi b?
Where lambda inverse.
Like in the argument of psi b, there is lambda inverse x in the transformation.
Yeah. So if you remember, when we did it for Lorentz transformation for the scalar field, for Klein-Gordon field phi of x, what we said is, if the Lorentz transformation is a symmetry, then the transformed field at the location after you have performed the Lorentz transformation, so x prime mu is lambda mu nu x nu, that should be same as the original field labeled by the locations before you have performed the Lorentz transformation. And so phi prime of lambda x is equal to phi of x, or phi prime of x is phi of lambda inverse x. So that's why under Lorentz transformation, a scalar field phi of x becomes phi of lambda inverse x. So that's why the argument there is lambda inverse x. But the spinor, so the spacetime location becomes lambda inverse x, and the spinor transforms by that lambda subscript half. Okay, whereas a vector would have transformed by lambda rho sigma. So there is a distinction between lambda half and lambda. Remember, lambda was for the vector representation and lambda half is for the spinor. Okay, sorry, that was not your question, but I hope I answered your question. You were asking why there is lambda inverse x, right? So you get no why?
Yes.
Yes. Okay. Okay. So this is the Dirac equation. Now our point is to check whether it is Lorentz invariant or not. So let's do that checking. Okay. So let's see how the first term would transform under Lorentz transformation. And so the first term is I gamma mu del mu psi. Okay, and the Lorentz transformation, it would become gamma mu. So this is del mu, so that's a covariant vector. So that would transform as lambda inverse mu del mu. So this is the transformation of this del mu, and then psi would transform as lambda half psi lambda inverse x. Okay, now this del mu doesn't act on this matrix, so we can take that matrix to the left. So this is equal to gamma mu lambda inverse, sorry, lambda half del mu psi lambda inverse x. Now what we can do is we can introduce lambda inverse okay, so no harm in doing that. Del mu psi lambda inverse x. Okay, now let's see. Okay, now these two also commute with each other, these two, so we can further write this down as lambda inverse gamma mu lambda half lambda inverse mu del mu psi lambda inverse x. Okay, now let's see what is this quantity. Okay, so what is that quantity? So okay, so lambda gamma mu lambda half this is nothing but equal to lambda mu nu gamma nu. Okay, so let's just prove that quickly. What was lambda half? It was exponential minus I over 2 omega mu nu is mu nu. Okay, and what is lambda? Lambda is exponential of minus I over 2 omega mu nu m mu nu. So if we take infinitesimal transformation, that means this condition boils down to, so let's write that down. I over 2 omega mu nu is mu nu. Let's use a different notation. Rho sigma is rho sigma gamma mu. Okay, since there is inverse, so plus 1 minus I over 2 omega rho sigma squared alpha beta. This is equal to exponential of that term, so it becomes 1 minus I over 2 omega mu nu rho sigma is rho sigma mu nu. So you should be able to now distinguish between what is what. So this mu nu denotes the row and column index of this lambda vector. Okay. So this implies identity will get cancelled out from both sides. Yeah, right. So the first term, okay, let me write down. So gamma mu, and then we are doing infinitesimal transformation. That means omega is small. We will retain up to first order in omega. So that means the left hand side we have two more terms, I over 2 omega rho sigma s rho sigma gamma mu, and the other term will be I over 2 it will be omega alpha beta, but instead of writing omega alpha beta, I am writing omega rho sigma, because it is not multiplication, it is addition. So even if we use same dummy index, it is of no confusion. And sorry, remember S is a matrix, so we have to be careful about the order. So, and gamma is also a matrix. Okay, so that is the terms we have on the left hand side. Gamma nu minus I over 2 omega rho sigma s, sorry, this is lambda. This is lambda matrix, which means we have M here, not S. M rho sigma mu nu gamma nu. Okay, so this will get cancelled out with that, and we have I over 2 getting cancelled out both sides, omega rho sigma also getting cancelled out, and so that condition boils down to showing S rho sigma gamma mu commutator is equal to minus M rho sigma mu nu gamma nu. Okay, so this is what we need to show. So remember, we have already figured out what this commutator is, so let us just copy that. Yeah, so here so this is what we have on the left hand side, and we also know what is M, right? The notation So M matrix was defined as I, let me write that down, so rho mu delta sigma nu minus eta sigma mu delta rho nu. Okay, so if I multiply this by gamma nu, m rho sigma mu nu gamma nu, what will it become? I eta rho mu. So gamma nu will become okay. So the commutator here we have is in terms of rho sigma and mu index. Just let me do the change here. So S rho sigma gamma mu will become I. This is just to make the comparison, nothing else. So rho is becoming mu here. So rho is becoming mu. Mu will become rho. So rho here and rho here, and nu is becoming sigma. So what is nu? Okay, sigma here, sigma here. So I'll just erase this. Okay, and so when I multiply by gamma nu, it becomes gamma sigma minus eta sigma mu. Gamma nu will become gamma rho. Okay, so you can see that we indeed have this particular relation. So which further implies that lambda inverse half gamma mu lambda half is lambda mu nu gamma nu. So it also has an implication. It implies that gamma mu transforms like a vector. Like a vector under Lorentz transformation. Okay, having said that, let's get back to our point. So we were here, just let me copy the entire thing down. Okay, and we will use this particular relation that we have proved. So therefore this is equal to I lambda half, this is gamma mu lambda half, this is lambda mu nu gamma nu. Okay, and we have lambda inverse del nu psi x. Now this lambda mu nu and lambda inverse nu mu will give us sorry, I shouldn't use same index, so let's use sigma. Okay, so I was saying that this lambda mu sigma and lambda inverse nu mu will give us delta nu sigma. Okay, and this then this sigma will become nu. So what we have ultimately is I gamma nu del nu psi lambda inverse x. Okay, so that's how the first term transforms. Therefore the Dirac equation.
Ma'am, can you please explain the last step?
Yeah. You can just write down one more line. Lambda of delta nu sigma comma sigma del nu psi lambda inverse x, and so sigma is becoming nu, and that's what we have. So the Dirac equation then becomes I gamma mu del mu minus m psi under Lorentz transformation becomes, first term is becoming lambda half I gamma nu del nu psi lambda inverse x, and the next term is just the spinor, so that transforms under Lorentz transformation by lambda half psi lambda inverse x. So this is lambda half I gamma nu del nu minus m psi lambda inverse x. So you can see, and this is equal to 0. So since we are getting this lambda half outside, and so that is why this is sometimes called Lorentz covariance instead of Lorentz invariance. Okay. Okay. So yeah, we can stop here. Let me know if you have any questions.
What is the last thing that you said?
I am saying that so unlike the Klein-Gordon equation, we are now having this extra lambda half outside. So in the Klein-Gordon equation, we just had the equation but evaluated, but labeled by lambda inverse x. But now we also have this lambda half outside. But this is still the Dirac equation in coordinate lambda inverse x. So which means it's 0. But because of the presence of lambda half, sometimes instead of calling it Lorentz invariance, it is also called Lorentz covariance. So you can say that Dirac equation is covariant under Lorentz transformation.
Okay. What is the primary difference between lambda half and lambda?
So lambda half is defined by exponentiating this S mu nu, which we have constructed by the gamma matrices which satisfy Clifford algebra, and the spinor transforms under lambda half, but any vector transforms under lambda, which is obtained by exponentiating. Where is that? Which is obtained by exponentiating these matrix representation of these vector representations, m mu nu, which we started defining, at the beginning, and then we defined the spinor representation. So there is difference between lambda half and lambda, this particular difference, but this omega remains same. So it shows that your spinor and your vector both are being transformed under same Lorentz transformation, meaning you are performing a boost along x, so you should perform boost for both spinor and the vector. So that's why this omega remains same, but the spinor transforms under lambda half, and any vector, 4 vector, transform under lambda. Okay.
No, I'm asking about the physical representations. Whether lambda is correspond to the Lorentz transformation, then lambda correspond to the same Lorentz transformation or something else.
Sorry, say that again. Sorry.
I'm asking about the physical representation, physical difference between lambda and lambda half. If lambda is correspond to the Lorentz transformation regarding the boost and rotations and all, what is lambda half represents?
So, okay, that's a good question. Yeah, as far as I understand, this S mu nu, that also satisfies the Lorentz algebra. So this S mu nu is also a representation corresponding to Lorentz transformation, but I'm not sure if that can be understood in terms of rotation and boost. Probably yes, but I have to check. I'm not sure right now.
Okay.
Any other questions?
No.
Okay.
Thank you so much.
Yeah, thank you for joining. Let's meet next week.
So, thank you. Bye.